Hello everyone. Good afternoon or good morning, depending on where you are. So I'm Corentin from Powersis. We will start the webinar very soon. Just wait a couple of minutes to let everyone join this session. So yeah, please wait a little bit. Hi everyone, thank you for joining. We are waiting a little bit before to start, but we will start very soon. Please be patient. Okay, I think we can start now. So hello again, everyone. Maybe Bharadwaj, can you confirm you can see my screen and that you hear me well, yes, please?
Yes, I can see your screen.
Okay, thank you. Thank you very much. So hi, everyone. My name is Corentin Jouvet. I'm part of the Powersis team. I will just introduce this Powersis webinar. And then Bharadwaj will take over. So this webinar will be about topology optimization of electric machines for e-mobility application. So thank you very much for joining this session. I will just say a very few words about Powersis. So at Powersis, we are a company supporting our customer in their electrification challenges, thanks to our expertise in several domains of the electrical engineering, such as electromagnetics, power electronics, multi-physics and system level design and simulation, CFD, so fluid dynamics, and finally power systems. We support our customers who are in two main fields, which are electric vehicle and grid application. One of our products we distribute to our customer to support them in such project is GMAG. So we are the official distributor of GMAG in Europe and also in the US, and finally in India. And this is how we support Volvo cars in their electrification challenges. And today I'm very glad to welcome Bharadwaj Raghuraman from Volvo Cars. So I will briefly introduce him. So Bharadwaj was born in 1993. He received a master's degree in electric power engineering from the Chalmers University of Technology in Gothenburg in Sweden in 2019. He was working as a powertrain engineer with the Mercedes-Benz Research and Development in Bangalore, India from 2015 to 2017. And then from 2017 to 2018, he was a project engineer of electric machine and inverter for Chalmers Formula students. And right now, he's currently a design engineer with the electric driveline department at Volvo Cars in Gothenburg, Sweden. His research interests include different aspects of electromagnetic and thermal design of traction motor in e-mobility application. So welcome, Bharadwaj. Thank you for accepting to give this this presentation for all our community today. It's an honor to have you here. And now I will let you take over to give your very nice presentation.
Thank you, Corentin. Thank you for such a nice introduction. Let me share my screen now.
Yeah, sure.
Can you confirm if you see my screen in full?
Yes,
full
I
screen?
can see. Yes, I can see it in
Okay.
full screen.
Great. So yes, as Corentin mentioned, I work at Volvo Cars in the electric driveline department, where we do quite a lot of electromagnetic simulations for our next generation electric cars. And one of the topics which I have chosen to talk about today is how we use topology optimization methods, which is quite a new optimization technique, especially in electromagnetics field, for enabling much better electric machines for electromobility applications. Going on to the content, I thought I will spend a few moments in talking about what is Volvo Cars' general strategy towards electrification, what are our goals, and what are our objectives, and then spend a few more minutes in the two types of optimization which we do in our team, which is parametric optimization and topology optimization, for both of which we use JMAG tools quite extensively. And then to end, I thought I'll also take a case study on how we use topology optimization to reduce the noise, vibration, and hardness characteristics of a machine. So starting off with Volvo Cars' objective, we believe that we should enable everyone to be able to move in a personal, sustainable, and safe manner. And in our team and in our department, we focus mostly on the sustainable aspects of this journey. And as many of you are aware of, the entire automotive industry is going through a shift with four main components: electrification, autonomous driving, connectivity, and shared mobility. And we contribute heavily in the electrification part of it, where we are transforming from a traditional internal combustion engine manufacturer to a fully electric vehicle manufacturer. And that requires a lot of research, and that is where JMAG is helping us to enable that. And in terms of what goals we have, as you can see, we have some very aggressive goals. We plan to be fully electric by 2030. And within the next 3 years, we also plan to sell 50% of our sales to come from totally electric vehicles, mostly battery electric vehicles. And we believe that there is no long-term future for an internal combustion engine. And hence, we are making heavy investment in this regard. And also to make sure that we are a fully sustainable company, we also want to be a climate neutral company by 2040. And to enable all of this, which has spoken, traction motor design is one of the key components of an electric driveline. And then one of the four main pillars of traction motor design is performance, efficiency, cost, and sustainability. Most of you might know that the first three, performance, efficient, cost, are some of the things which everyone deals with when they do a design. But we in Volvo Cars believe that sustainability has to be taken up from the concept level to make sure that we are accountable to the nature on what we do as a company. So when it comes into machine topologies, we are investigating several different topologies at once. When it comes to permanent magnet machines, We of course have rare earth element based permanent magnet machines, but now more and more we are looking more into non-rare earth permanent magnet machines. And when it comes to induction machines, to make it more sustainable, we are looking at aluminum rotor cage induction machines. And if you want performance, then we're also looking at copper cage induction machines. And to go into much more sustainable solutions, we are also working on synchronous reluctance machines and switched reluctance machines as well. Going forward, I thought I will briefly describe how an electromagnetic design process takes place within our company. And what we believe in Volvo Cars is that we need to optimize the system rather than a subcomponent of the system. And hence, all our design efforts are to make sure that at the end, we have a system optimized solution rather than a component optimized solution. So if you can see the flow chart on the right, here you see that we get some system requirements. Basically, that means you might get peak torque requirement, maximum speed requirement, and maximum power requirement. And once we get these kind of system inputs, we start with what we call initial dimensioning of the machine, where we try and come up with what is the maximum packaging space which we require to fulfill these requirements. What is the DC bus voltage, which is also driven by the battery teams. And thirdly, what is the amount of current we think we might need from the inverter, which is again in collaboration with our inverter colleagues. So once we have this initial dimensioning done, we end up with a concept where we can fulfill the performance requirements, but still not everything else. We still have to look at thermal aspects. We have to look at sustainability, and most importantly, the cost as well. So once we start with initial dimensioning and finish with some packaging constraints, we bring that up into a much bigger scope of work, where we also include thermal studies, where we look at what is the steady state temperatures for different drive cycles, and also look at different drive cycles in terms of efficiency and range, like WLTC cycle, US06 cycle, and so on. And then this is where we use JMAG Designer quite a lot, where we do a multi-objective genetic algorithm approach, where we try and meet most of the criterias. And once we have a candidate, what we call a detailed design candidate, we send it out to our system colleagues, where they get different inputs from all other branches, such as the inverter guys, such as from the battery. And then we do a system evaluation. And from the system feedback, we revisit initial dimensioning of the machine if required, or revisit our multi-objective genetic algorithm-based detailed design if required. And as many of you might know, an electric machine design is an iterative process. So we do several of these iterations until we can converge to a solution which we think is best for the vehicle which we have chosen to implement this for. Moving further, when we want to do initial dimensioning, we take the help of JMAG Express, which is quite a fast tool for us to evaluate different boundary conditions. So we might want to evaluate for a certain torque and power level, whether a PM machine is more suitable, or an induction machine is more suitable, or a SynRM machine or a synchronous reluctance machine is more suitable. And JMAG Express, with its fast calculation methods, enable us to do that quite rapidly, so that we can come to some sort of conclusions on what are the inverter current levels we might require, what are the packaging space we might require to fulfill these requirements. And once we do initial dimensioning, as I said earlier, then we go to a detailed design concept, and that is where we use parametric optimization. And here is a flow chart of what we generally use. So first we start with JMAG Express, as we said earlier. So we start with a model which has got from the initial dimensioning approach. We take the template out of the JMAG Express and then implement that in JMAG Designer, which is a fully finite element analysis tool. And we customize all the parameters which we think is of interest to us to optimize, we put in an optimization process with different objectives and different weights, and then we do post-processing of these data, and then send it out to system studies where we analyze the entire system performance and system sustainability, and then start over this process or take some shortcuts in this process. To explain this a bit more, I thought I will give an example of what we do. So here you see that we are trying to optimize a 2-layer U-shape PMSM machine, which is made up of rare earth metals. So we start with JMAG Express. We do some initial analysis. We come up with some boundary conditions in terms of length or stator outer diameter, maximum current rating, and so on. And then we use the templates from JMAG Express, and then we move over to JMAG Designer, which you see on the third picture here. And we use JMAG Designer to implement our own parameters, which are, we use some parameters which JMAG comes with automatically, and then we further improve it by adding our own parameters. And then we customize the parameters, both CAD parameters such as the thickness or the width of the magnets or the stator outer diameter, but also the magnet grade, the magnet volume, the steel grade, number of poles, and so on, so that we are able to look at many different designs before we come to an optimized solution. And then once we have the parameterized model, what we do next is to give objectives for optimization. And as you can see, perhaps it's a bit smaller, the picture which I've shown here, but one of the optimization objectives is to reduce the amount of neodymium iron boron magnets which we use. Second thing is to achieve the torque which we have asked the machine to achieve. Third thing which we try also look at, especially for this U-shaped magnets, is what is the demagnetization behavior of this machine. So we try to limit the amount of demagnetization this machine can take. And third and fourth, we try to reduce the length of the machine to make it more power dense and torque dense. And once we run this optimization, generally we run it over a cluster with many solvers, and then roughly, as you can see, roughly hundreds to thousands of cases. And then we reach some sort of steady state behavior in our optimization process. Then we use the JMAG tools and other tools to post-process this data, make different Pareto curves, and then extract one design which is the best out of these many cases. And once we have that design, we then run much more analysis on it, say noise and vibration analysis, structural analysis, demagnetization analysis, even a thorough demagnetization analysis. And then once we are satisfied with how the machine is behaving, then we create what we call a system model. Basically, it's a table-based model where you have torque, speed, temperatures, voltages, and so on. And then the system model is extracted and sent out, and then the system team here will analyze this with the data coming from the inverter, data coming from the battery, data coming from the vehicle project. And then we look at what are the different criteria which we wanted to satisfy, and how are we satisfying this, and then we iterate this procedure based on that feedback. So this is what we do when it comes to parametric optimization. I suppose many of you who are in this call also do this. What we do more than this is we also employ topology optimization methods for some specific applications in our electric machine. But just for the benefit of everyone here, I thought I would go a bit on what does topology optimization means. So as you can see in these 4 pictures here, the basic idea of topology optimization is you divide the region of interest into many different regions, maybe iron, maybe air, maybe permanent magnet, and so on. And then you ask the topology optimization function in JMAG to place the iron, air, and permanent magnet in such a manner so that your objectives are fulfilled. So this is what is called topology optimization. And once you pair it up with something like a genetic algorithm-based topology optimization, then you see the real benefits of why we want to use topology optimization. As an example here you have a single layer flat magnet configuration on the left, and the red region here is of interest to us so as to design a flux barrier. And then here we use a genetic algorithm-based approach, and you can see the results for different generations. So after 50 generations, you see some sort of a design which seems rather okay, but still there are quite a lot of things to be optimized, especially the air pockets around the magnets, which is becoming better and better as the number of generation goes up. And you can see that already in generation 100, you are pretty much close to the optimal solution. So this is what is topology optimization. Here in Volvo cars, especially in our team, what we use topology optimization is for reducing the noise levels in our electric machines, even though electric cars are less noisier compared to our combustion cars, but we still want to reduce a certain frequency components, and that is where we use topology optimization methodology to achieve that. So if I can go through this flow chart here, what you see is that we first start off with a 2D transient electromagnetic simulation, and then we extract what we call stator tooth forces. Basically, it's the forces acting on the teeth due to the armature reaction and the rotor flux. And then once we take the frequency analysis of the stator tooth forces, we include that in a structural dynamic analysis for the complete axle, where we have the housing, where you have the gearbox, and so on. So we also include the mechanical aspects of this machine and the surrounding in which this machine will operate. And then we perform acoustic analysis, where we look at what is the noise level which is being generated. We validate our methods through measurement. And then once we have the measurements and then frequency analysis, we go back to a topology optimization and optimize certain features in our electric machine. As a case study, I thought I will present one of things which we did quite a time back, which is also present in one of the IEEE conferences as well. So on the right side here, you can see a 48 slot 8-pole interior permanent magnet machine. And as you can see, we have a 2-layer V-shape permanent magnet machine. And in the middle, we have what is called a flux barrier, which is marked in black. And the purpose of this flux barrier is two things. One is to reduce the mechanical constraints on the magnet. And the second one is to improve the noise levels of this magnet. So the goals of this optimization, which we ran in JMAG, is to design this flux barrier in such a way that the motor performance is not disturbed, and it should not be more than 2%, but 2% is still a very high margin. We prefer that the motor performance is not degraded by less than 1%. And since this is a 48 slot 8-pole machine, of course, we will have the 48th order, temporal order, and then we have other orders as well, like the 8th order, the 24th order, and so on. So mainly our target is to reduce the 48th order harmonics, and then also reduce all the other harmonics present, all the other main harmonics present in this machine as well. And we give different weights based on what we are trying to achieve. As you can see, we have weights of 2, 5, 4, and 1 based on what we want to achieve in this optimization. And how do we do this study? We use a spatial temporal order analysis, meaning that we extract these stator tooth forces out of the JMAG tool, and then we run a 2-dimensional Fourier transform approach, where we break down the stator tooth forces into spatial harmonics and time harmonics. And that is the graph you see on the right here, where you have the spatial orders going from 0th order to all the way up to 16th order. and then the temporal orders between the 0th order and as many orders you can have in time harmonics. And one thing which we should understand here is that the amount of noise which can be created by an electric machine is directly proportional to the fourth inversely proportional to the fourth square of the spatial order, meaning that any or spatial order over 0 is of very little significance to us. And what is of most concern to us is the temporal orders or time-based orders. So that is why we mainly concentrate on the 0th spatial order, and then we try and concentrate on the 24th temporal order and the 48th temporal order. And what we do here is that we do this analysis where we extract these stator tooth forces for different speeds, maybe for a max line plot, and then we plot these curves as shown here, where we track these orders as a function of rotational speed. And this is one way for us to understand what is the noise levels in the machine. And then to make sure that what we're doing here is actually correct, we also verify our methods. We have anechoic chambers where we do tests on our machines, and then we measure these noises of these specific orders, in this case order 24 and order 48, and then we compare these orders with our CAE calculations done on JMAG. And on the bottom here you can see the measurement versus CAE calculation, and you can see that there's quite a good match between what we predict using JMAG tool and what we have measured in our chambers. So coming back to the problem which we had, which is to reduce order 48 and then also to reduce the sum of the other tooth forces, I would like to show you some results. So we started with this design as the initial seed for the optimization, and after a couple of thousands of generations, we ended up with this design, which is quite genetic in nature. And this kind of an optimization method, which was only possible due to topology optimization, helped us to reduce our 48th order temporal order by up to 50%, and also the tangential order as well. And here on the right, you can see that we have 6 Q segments as well. We, on top of topology optimization, we also used the JMAG to analyze different skew segments, what are the effects of different skew segments, and so on. And here you see the effect of this change through topology optimization on the noise levels, on the forces level, which will translate into noise levels. And further on, what we could also see is that by doing this topology optimization, we were able to stay within this 1% of performance degradation, and we were able to even achieve 5 dB of noise reduction, and then make sure that our vehicles are much more better compared to what we had designed earlier. And I think this is one of the main aspects of topology optimization, where the results can be quite interesting and then can lead to quite drastic changes in the problems which you're trying to solve. As a reference on what I have said so far, we have published this paper last year in the IECON conference 2021 with the title shown here, and you can look through this and then find more information on what we have exactly done. With this, I would like to say thank you to everyone for listening, and then I'm happy to answer some questions.
Thank you very much, Bharadwaj, for this very nice presentation. So yes, we have some questions already, but it's still time to ask your question. So if you want to ask a question, you can use the Q&A panel or the chat panel in Zoom, and we will just answer it right now. So let's go through the first question, Bharadwaj, if you are okay with that.
Sure.
So you can open the chat panel. I will read the question. Mm-hmm. So to make to make sure you know which one we are talking about. So the first one is about non-rare earth permanent magnets. And the question is, does non-rare earth permanent magnet means that it's ferrite magnet-based machine?
Yes, I would say 90% of the time it is ferrite magnet machines, but there are different solutions also coming up where you have plasto bonded neodymium magnets and so on, which are heavy rare earth metal free, and there are different options also in that. So yeah, 90% of the time it means ferrite magnets.
Okay, thank you. The second question is regarding the topology optimization of the rotor that you have shown. Do you take the mechanical stability of the steel bridges into account in the optimization? And one more question, how long does it take approximatively to reach an optimal rotor geometry?
Yeah, on the steel bridges, yes, we use the JMAX mechanical toolbox in JMAC Designer to account for the stability of the steel bridges in our optimization, and the time it takes to reach an optimal design is really dependent on number of parameters you would like to play with and amount of solvers you have. So I don't really have a specific time which I can say outright.
Okay, thank you for the question. Next question is the bidimensional Fourier transform performed with GMAG?
Yes, yeah, the two-dimensional Fourier transform we are performing within JMAG.
Thank you. So we have a lot of questions coming still. Let's take the next one. How long did the optimization take? So in terms of time, I guess.
On this particular case, we ran several different loops of optimization and to come up with a solution which I have presented here with many different loops and many different teams involved, roughly 1 to 2 weeks.
Yeah, thank you. I just want to add that when you are, of course, when you are running optimization with GMAG, the time will depend on how many Ks you will be included in this optimization, and also how much you will parallelize will make a big change of your calculation time. Next question: what is the source of spatial order and temporal order?
Sorry?
What is the source of the spatial order and the temporal order?
Okay, I mean, this has to do with the harmonics created by the non-homogeneous rotor structure.
Okay. We have a next question which says, which method is utilized for the topology optimization?
Yeah, I think I've already said that before. We use a genetic algorithm-based topology optimization technique.
Okay, thank you. Next question says that synchronous reluctance machine will be suitable for electric vehicle application, but what is the effects of the power factor?
Well, yeah, even though it's a bit out of topic of this presentation, yes, synchronous reluctance machines have lower power factor. We know that, but it has certain benefits in terms of sustainability.
Okay, yes, thank you for the question, even if it's outside the scope of this presentation. Do you know how have you selected crossover and mutation rates of the genetic algorithm?
Well, it is based on experience, I would say, and also how many parameters you have in your optimization. I don't remember on top of my head how many we have selected for this.
Yeah, so if you need any help for selecting the parameters of your optimization, the GMAG team can help us on that. We have experience, or based on how much parameters you have and your objectives, we can try to give you some advice. So feel free to contact us for this. Next question is the topology optimization is based on level set method?
I do not understand I don't know what is level set method. I'm sorry. Maybe
Okay.
Didier can help.
Yes, maybe Didier, do you know that? Okay, Didier, we cannot hear you at the moment, but maybe you could answer this question later. If you just let me know when you are ready. So we will try to get back to this question later.
Oh, can you hear me?
Yes, we can hear you now, Didier.
Yes, so can you repeat the question? Sorry.
Yes, the question is the topology optimization based on level set method? Do you know what is level set method?
No, what do you mean by level set method?
Okay, so maybe we can ask the person who has this question more detail, and maybe we can come back to this question.
Yeah, because I know that into the topology optimization engine, so you have several methods, but inside GMAC we are using the density method and on-off method. So can you explain me in detail what is level set method? Yes.
Okay, so if the person who asked this question wants to give more detail, we will get back maybe later on that question.
Okay, thank you.
And in the meantime, we can go to the next question. What could be the effect on performance when the acoustic noise reduction?
So as I said, in our case, we try to introduce a flux barrier in the d-axis of the machine, which will reduce the performance, and that is why we use the topology optimization method to make sure that we don't degrade the performance by more than 1%.
Okay, thank you, Bharadwaj. Our next question is about, let's say, maybe more related to manufacturing. How are the magnets fixed in the rotor holes and how it affects the structural response? Do you have any idea?
Generally, in manufacturing, the magnets are either only pushed in or also glued with a thermally conducting glue. So perhaps that would answer your question.
Yeah, and in this case, have you made any analysis on how it affects the structural response of the machine?
Yes, but I don't have enough information right now to share it with here.
Sure, no problem. I think it's also maybe a bit outside the scope of your presentation. No problem. I don't know if you will have also that question is which type of genetic algorithm is used?
Well, we use a multi-objective genetic algorithm method where we have different objectives with different weights approach.
Okay, thank you. The last question, or maybe not last question, you can still ask some question if you want, but until now, the last question is, would it be interesting to have a loop between parametric optimization and topology optimization?
Well, we are doing that in a manner that where we start off with a parametric optimization, come to a solution which is very close in terms of performance, efficiency, and sustainability, and try to use topology optimization for very special cases such as noise and vibration.
Okay, thank you. We have a new question that just arrived, which says, you have done your optimization based on Maxwell stress tensor from flux in the middle of the air gap or by structural simulation in GMAC?
No, we use the Maxwell stress tensor in the middle of the air gap.
Okay, and how accurate it could be to do an optimization based on this stress tensor?
Well, we use the Maxwell stress tensor. So, and we have got very very good results when we also do the measurements.
Okay, so you have compared the GMAC result with the measurements, right? How you measure the suitability in GMAC software?
I don't understand that question.
Yeah, I don't understand. What do you mean by suitability here? Or maybe it's sustainability, I don't know. So yes, if you, Ganesh, if you can add some detail of your question. So in the meantime, we can go to the next question. Do you use nodal forces to evaluate structural aspects?
Yes, we use many different methods. One is nodal force and also the Maxwell stress tensor in the air gap.
Okay. Okay, maybe we can add some details. So we have some more detail about the question about level set, Didier, mainly for Didier. So it says that level set is another type of treating the evaluation of meters holes in the design domain, combining shape sensitivity method and descent method, but not with genetic algorithm. So I guess this method is not used in GMAC.
Yes, so for the moment, we have not implemented this method into GMAC. So into GMAC, you only have a simp and on-off method. Yeah.
Okay, so I think now we have covered all the questions we had. So maybe it's time to say again, thank you very much to Bharadwaj for this very nice presentation and very interesting presentation of an innovative way of designing electric motors, which is very nice. So yeah, thank you. I would like also to mention that we will organize several webinars in the coming weeks on electric motors topics. So if you want to register, feel free to have a look on the PowerSys website, the events and webinar sections. You will have the list of all the webinar. And if you have any question about the presentation today or about GMAC, feel free to contact us at PowerSys. And if there is any specific question about this presentation, we will forward the question to Bharadwaj. So thank you very much, everyone. I don't know if Bharadwaj, you want to add anything?
No, thank you for the opportunity, PowerSys, for giving us in Volvo Cars to show what we are trying to do here. And thank you, everyone, also for participating in this webinar.
Thank you very much. Have a very good day. Bye-bye.
Bye-bye.